And welcome to today's edition of Cota Access. Thank you to everyone who's joined us today. For those of you who are joining us for the first time, Cota Access webinars offer in-depth, detailed discussions with industry leaders and thinkers on a variety of topics around tech, business, and the latest cutting-edge trends across the world. Today's webinar focuses on advancing physical AI and ensuring safety and reliability. We'll be discussing a whole bunch of topics, but focusing on the challenges that physical AI faces currently and how advanced math and AI can help resolve some of these challenges. I'm Vikram. I'm a principal at the Cota Capital in the Cota Capital investment team, and I'm joined this morning by Behrooz. Behrooz is the founder and CEO of Atomathic AI. Atomathic is a leading physical AI sensing technology company, which is building advanced AI platforms built around proprietary mathematical algorithms, which really transform how machines perceive and interact with the world around them. Behrooz also has a depth of experience before that. He's been founder and CEO of Atomathic, which he led to an IPO and then an acquisition by Qualcomm, as well as founder and CEO of Quantana, a leading Wi-Fi tech platform that he also led to an IPO and then a billion-dollar acquisition. Behrooz also has a PhD, 40 plus patents, and is uniquely placed to share his insights around physical AI. Thank you, Behrooz, for joining us this morning.
Thanks for having me. I'm really glad to be part of this conversation with you, Vikram, and Cota team.
Awesome. So maybe let's start at the very beginning. So we're talking a lot about physical AI. We're hearing it in the news all the time. Tell us a bit about what physical AI actually is and what's the state of the union for the world of physical AI right now.
Right. So everyone has heard of AI and LLMs and in current AI system that everyone is familiar with, it operates on texts, essentially, digital tokens. And all the innovation that has come through this foundation of language model that is being used. But the thing about regular AI or LLMs is that they're operating on text or text sequences, meaning of texts. So everything is confined in the text domain. And now, of course, there's a lot of work that's going on in terms of reasoning, but put that aside for a second. What we're looking at on physical AI, it's that now you have a robot or an entity that's interacting with the physical world. And physical world is about physics, geometry, acceleration, motion, all of these things. And so you put a robot in the middle of all of this, and depending on the expectation of what it's supposed to do, the very first thing that it has to do is to sense. Now, in the world of robots and interaction with the environment, that interaction is continuous in time, meaning that there are no discrete values, such as a text, for example, and or they or whatever. It's all physical information that has gone translated back and forth between sensors and what is sensing and sending it to the farther up the chain. So the issue with the continuous world is that the number of possible scenarios could be, depending on the complexity of what you're trying to discover, could be infinite almost, because there are just so many possibilities. And that boundary condition, that variation in sensing, obviously cannot be trained on because there are just so many of them to train on. And sometimes you don't even know. So the modern way of thinking about physical AI is that we equip it with enough reasoning and thinking and mathematics and physics that when it encounters an unknown environment or hasn't seen before or hasn't trained on before, it can figure out a way to resolve it. So that's kind of fundamentally what this is all about. Um, and this year, I think in 26 is by some is called physical AI year, in the sense that NVIDIA published a whole bunch of stacks that talks about how physical AI comes. So it's a new field, and there's a lot of work to be done. But the concept of physical AI is you have to interact with the environment, and just that interaction with the environment inevitably brings you to sensing because you have to sense. There's no communication between a car and a road, or a robot in agriculture trying to pick a fruit. So it has to be understood. So I say, for example, you could have a brilliant brain like an Einstein, but if you don't have glasses, you can't read it. You read the material. So you need the sensing, and sense is for the humans as well. Sense is such a big part of our brain and brain functions.
Yeah, so let's dig a bit more on that and to use the same analogy. So there is sensing or vision and there's the brain. So what are some of the players doing on both these fronts and what remains to be solved is the next frontier to advanced physical AI in the next few months and years?
Yeah. So again, physical AI is really we are at the beginning of the you know, innovation. A lot of work's been done around uh, cameras, because cameras are really good method of capturing information, but they don't have a number of other attributes. So, for example, with images, you cannot tell the distance, you cannot tell the resolution, you can't say any of these things about it. You can't say if it has a smell or sound. That is part. I mean, obviously, cameras play a critical role, but it's not the complete role. And so, as such, you need more sensors to collect more data. And those data sometimes are really critical for the functionality of the robots or whatever system we are trying to automate or make decisions real time on its own autonomously. It could be a drone, it could be a car, a self-driving car. In agriculture, it could be picking fruits or discovering weeds or disease on trees. And so in defense, obviously, as we are looking at enormous number of challenges in terms of hypersonics, complexity of a lot of drones together. There's always something that we don't know, and the sensing is the issue. And camera cannot necessarily play a final role. There are a lot of other things that depending on the solution that we're after. Now, I have to say, like, for example, with the physical AI, as for example, NVIDIA kickstarted 2026 at CES, and they introduced foundational models, simulation environment, all of that. And I'll briefly touch about some of these. For example, foundation model like Cosmos is similar to what we have, and I'll talk about it when we get to it, like we call Acer. So.
Got it. So most of the applications you spoke about, whether it's defense, agriculture, mobility, etc., they need reliability, stability. So how do you see physical AI models evolving to bring that stability and accuracy? And what's the thinking modes that are needed to deliver that?
Right. So as I mentioned, depending on the role of a sensor, and in case, let's go with what we are actively working in a couple of fields, such as autonomy, autonomous robots, autonomous driving. Um, when you get in challenging environments such as fog, poor lighting condition, dust environment, and this could be also in agriculture or other field, outdoor field. Um, you don't have obviously enough information from cameras, so then you're going to have to focus on other sensors to discover what's out there. In case of autonomous driving, safety is super critical in terms of how a car is driving on a road and whether it's going to hit a pedestrian or not, a vulnerable road users or VRUs we call it. And so then the sensors become super critical outside of cameras that we're going to have to now discover uh, potentially a child next to a school bus. These are really scenarios that could lead to um, fatal accidents or really damaging accidents. And so I want to give an example. For example, this problem in radar is really complicated because it's an ill-posed problem. Um, and I'll give you an example by ill-posed, but the issue uh, is so serious that, for example, Tesla decided not to put radar because they could not get consistent results out of their radar system. And as such, they're kind of compromising a bit of safety in favor of reliable performance. And so now coming back to what I mean radar issues in the industry, which is, as I mentioned, is ill-posed inverse problem. Maybe a simple example can illustrate what I mean by ill-posed inverse. Suppose, and it's a completely different kind of example. Let's say you are in a school and you're looking at students going to classrooms, and you have sensors that with some accuracy, let's say plus minus 5 or 10 centimeters, measure the height of the students that randomly measures, and then another sensor that measures the weight of the students plus minus a kilogram. And then after a few set of measurements for a few days, you ask, okay, how many students are in the classroom and what's their weight and height? That's an ill-posed problem because you don't know. You didn't have enough accurate sensor measurements and enough of them to know exactly how many. All you know, you have an average weight and average height based on some noisy measurements. But it ties to the work that we've been doing, which is called atomic norm. Atomic norm is a mathematical concept that works on specifically on ill-posed inverse problems very well. And basically, uh, just like the example I just mentioned, we can represent students as an atom, and it could have, we can assume certain height and certain weight without any kind of um, dependencies on the accuracy of the sensors. So remember, I said the sensor could be plus minus 10 centimeter height measurement, plus minus a kilogram, but the distribution of people in the classroom could be anything. And then the other thing that is of interest to us is that, okay, how many students? Now, we go to another set of problem it solves. Atomic norm is based on a mathematical framework called sparsity. We could not possibly, if there were 300 students or 500 students in that classroom, it's not sparse. But if it was 10 students in that classroom, it is sparse. So then we would be able to, through methods such as atomic norm, figure out how many students are in the classroom, what's their height and weight, because uh, that's the method of solving. We can assume certain heights and certain weights, and then find out what possible combination of the students actually give you the result. And similar things happen in radar problem. In radar problems, you have a finite set of sensors or antennas, and then you have a lot of data points in the field of view, and you're asked to discover what's in it. And this is how atomic norm works really well because it solves the ill-posed problem. But it needs one more layer on top of that. And we call that in our uh, processing, we call ACER, which is based on reasoning. And the reasoning is pretty important, and we don't think anybody has done it yet for radar. We are the only company, it appears, that we have done it. Similar to what NVIDIA did for Cosmos and then reasoning on the on their platform because they have trained on a lot of course, video data. We use our Acer to experiment and decide and reason from physics-based reasoning that, okay, what's possibly these returns mean? And then with sufficient permutation of the reasoning that looking at different possibilities, we create what we call, in LLM, we call it chain of thoughts. In our language, we call it chain of causalities, in the sense that we experiment with different experimentation and then look at the results real time. And then we say, okay, what possibly explains this result? And through physics informed reasoning, then we are able to kind of discern what's ghost, what's phantom objects, and then what's left is the real detection. And that's critical because to our knowledge, you do need this kind of reasoning in case of at least autonomy to be able to discard what's not real. And there's always competition in terms of making the sensors cheaper, faster, and so yeah, if you had to, you could spend $20,000 per sensor on a radar on a car and very big, you don't need those reasonings, but you're asking, a percent of the cost and a few percent of percentage of dimensions, and then now you're asking a very complex question, and those can be resolved through reasoning. So, and you can't solve it by, for example, vision, language action. For example, what NVIDIA has, it's those kind of things are solving the questions of what's happening in the field and what are the intentions of the pedestrian on the road. But when you don't see anything, and then you don't have the reasoning architecture for radar, then still you have nothing in a sense that you're still stuck. So you have to go through that path in order to be able to resolve it.
Got it. And I'm not nearly as technical as you. So from what I took away, it seems like the an equivalent analogy is something like seeing a blurry image or seeing a very cluttered scene and being able to pick out the right physically possible, probable scenarios and reason and build a chain of causality. Is that a fair
Yeah,
understanding?
that's correct. Yeah, you're absolutely right. In a sense that in a cluttered environment where there's so much signal returns that overwhelms the radar systems, and so you do need a thinking mechanism to discern what's real and what's not real. If it was going to my original comment, if there was one student in the classroom, you can always say it's one student, and there's no issue. But when there are hundreds or tens, depending on the sparsity requirement, the number of measurements, that becomes an issue. So in a cluttered environment, you have a lot more signals coming back and very few antennas to resolve them. So you're absolutely right. That is the, and radars are important because in anything that is related to optics have issues. For example, LiDAR, they have issues in fog environment or snow environment. So so you do need all this hierarchical sensing system to get the final decisions out. Yeah. So, but you need all three of
Maybe
them essentially.
Yeah, maybe let's touch upon that a little bit. So there's cameras, there's LiDAR, there's radar. All of them have their pros, cons, advantages, disadvantages. So tell us a bit more about how you think about the sensor hierarchy or the unified perception engines.
Yeah, I mean the final optimization goal of any autonomous driving in a highly regulated environment, such as transportation, is safety. And we've seen safety could come back and be really important for the society at large. And every time you see an accident or fatal accident, the company in charge of it, it's really scrutinized in a big way. And the populations, they have their skepticism high. And so in terms of the hierarchy of systems, depending on the level of autonomy, there's a redundancy requirement, and then there is making sure everything is highly reliable. But it seems to me that obviously cameras are a really critical part of the perception system, and they are the king of the whole thing. But you also do need radar because that's the only sensing system that actually measures distance correctly, measures accuracy, measures Doppler or velocities. Um, and then you want to make sure that these guys, the problem with radar, as I mentioned, is the reliability factor that could cause decision mismatch at the perception layer. And so more and more on ADAS, people are, which is the kind of semi-autonomous level 2 or level 3, people are settling on, let's just go with high quality cameras and then radar. And so that's becoming, it seems, a firm decision. Now, once you go to level 4 autonomy, the general consensus is that because there's no driver in the car, you have to be able to have multiple redundancy in order to guarantee highest reliability decisions. And that's, for example, how Waymo is shining so well because they have LiDAR, radar, and cameras, and they all obviously the one out there is Tesla that is claiming they can solve only with camera, and we have to wait and see if that's really going to come to fruition. I don't think it is possible. I mean, at least that's the reasoning that I see from most other people. But the bottom line is that cameras are the number one, but you need, depending on the interaction that you have to have, whether it is in the field, outdoor, you do need another measurement that sets when camera doesn't do a good job or it's not its native behavior. So its native behavior is not measuring distance, is not measuring the angles of things are moving in certain direction. So uh, yeah, so I think at least in the field of autonomy, we think it's absolutely radar is a must.
Got it. And then I'm going to go back to a couple of terms you used in the earlier part of this conversation. So you said physics informed or physics aware computation is needed, and
Mhm.
you need sort of reasoning
Yeah,
which is
very good. Yeah.
deterministic. So tell me a bit more
Yeah.
about the how this interacts with LLMs and the probabilistic models. Is there anything you can pick up from that and leverage, or how does the interaction work?
Right. So going back to atomic norm, in case of radar, we define an atom to be a physical response of radio wave, electromagnetic wave, which is a physics, we call it Helmholtz equation, and hits a target, and we assume it's a point target. So that's the definition of one atom. So every point in space and can be defined a priori that what is its signature, given the antenna is what they call point spread function, or the signature of the array. So we essentially know what each atom looks like in the whole field of view. So when we illuminate the field of view with radar signals, then we are asking this fundamental question: what atoms are in this return? Because the return is only one return, and we are trying to figure out how we can decide how many atoms and where they were to form this image or this return. Now, the beauty of this architecture is that each atom is a physics-informed response anyway. So in other words, by definition, our approach is physics-informed. So every atom has a physical meaning in space, time, speed, etc. So we can fully define a physics-informed response. Now, when we sum all of these things, there are behaviors that are imperfect, such as antenna system. There are a lot of issues that I want to go into this detail right now, but and those imperfections cause aliases and phantoms, and that's what we need an additional layer on top of atom to generate other possibilities of atoms that form that response. So in other words, we are completely working in the field of physics-informed domain, and we're always looking for plausible definition or plausible explanation of what just happened. And we generate scenarios that again ask what is physically possible. In other words, none of our scenarios that we generate and we ask the reasoning system to figure it out is based on some sort of hallucination in terms of what happens in LLM. These are everything that is generated physics based, and because it is physics based, we can trust it, and it's trustworthy and reliable. And so this is one of the strong advantages of using the method that we are using, because everything is physics based.
Got it. And then all these applications that you've spoken about, latency is the enemy of good decision making in these applications. So maybe touch upon ADAR and ACER and how you're thinking about both fast and slow responses that cover all the probabilities.
Yeah, thanks. So, so we are again like LLM. We also follow similar concept in LLM and cognitive thinking. There's fast thinking, which is immediate response, and then slow thinking, which is considered as multiple options before responding, and that falls to our the two products that we have, ADAR and ACER, and how they work together. ADAR, which is the fast response or fast reasoning thinking, essentially returns what it thinks it is the most optimal solution for a given condition. So that is critical because we are not leaving any information out. We solve this first thinking optimally, but we know when you solve the first snapshot of what you're looking at, it could be filled with ambiguities and ghosts, etc. So, but we know what we created is follows. It can be completely traceable with physics. Then we generate multiple scenarios, and that's ACER, which is the reasoning. And I mentioned it's somewhat similar to Cosmos. You can think of that what NVIDIA has. This is a physics-based reasoning system for radar. And so if you had to run a parallel, that's what Cosmos does. It's a word model and from NVIDIA's lingo. So for us, ACER is similar in a sense that it reasons what's possible based on physics generated, and that physics generated happens at ADAR. Now, one of the biggest challenges for us that since we started Atomathic almost 8 years ago is to really speed things up incredibly fast. So from the initial time when we started it to now, I would say we have a speed of over 100,000. So this is decisions with robots has to happen in real time. And real-time decision-making is also the name of the game for physics and robotics, because you are in the middle of making quick decisions, whether you slow the car, you move the lanes from one lane to another lane, or slam on the brake. All these decisions are happening in the orders of tens of milliseconds. So, and that's some of the biggest breakthrough had to come in order for us to make ACER and ADAR to work.
Got it. And we're coming up on time, so maybe let's touch upon one last question. Um, you've spoken about a bunch of applications in autonomous vehicles, robotics, defense, etc. Where else do you see this being used, and what's the realm of possibility for physical AI technologies or ADAR research?
Yeah, anything that has to do with sensing, essentially. And typically, when the problem is ill-posed, you do need a mechanism to recover sparse signals and then make a decision that what is it or what was it that we just saw. And again, you can go from robotics. It could be agriculture. It could be, and these are not simple problems, but essentially, give you an example. If you have to make a decision to whether you're a robotic nurse or a robotic fruit picker on a very sensitive fruit, you have to within a few centimeters or a few millimeters even be accurately picking or touching the object. Now, the more accuracy you need, the sensors are becoming more and more expensive. You can't do that. You can't really put super expensive LiDAR in an agriculture environment because it's a dusty environment. So you do need a radar, and then you need to use estimation approaches based on atomic norm, for example, to decide exactly how sensitive their accuracy is, and so on. So you can go from agriculture to as I mentioned, defense, semiconductor for other things. There are a lot of approaches that we are experimenting with at Atomathic, and we think it has a lot of room.
Got it. Thank you, Behrooz. This was super interesting. We learned a lot. Thank you so much for taking time out this morning. And look forward to seeing all the amazing stuff you do in physical AI in the next few months and years.
Thank you very much. Thanks for having me.